So, what we have achieved from Schrodinger equation for hydrogen like atom. So, we have achieved that energy expression E n equal to minus mu z square e to the power 4 divided by 2 n square h cos square, which is same from as we achieved from the Bohr model, but additionally we have got this eigenfunction psi n l m. So, now I will not write m l, okay, just write, I will write simply m, okay. In place of m l, I will just write m, okay. So, we got the wave function, eigen wave function solving the Schrodinger equation for hydrogen like atom is basically in this form R n l, it is a function of R, then theta l m, function of theta, and phi m, function of phi, okay. Where theta phi m, the form of phi m is basically e to the power I m phi, and form of theta, it is l m, it is theta, its form is I think its form is like sin m theta. So, this the mod m means positive value, because m value is plus minus value. So, here just positive value, and this then some polynomial in cos theta, okay, polynomial in cos theta, okay. What is this? This basically this Legendre polynomial, okay. So, that is so it has it's as a whole in general it is looks complicated, but for different value of L and ML, so this form are readily available. So, that we will use whenever we need, okay. So, and then R n l function of R. So, here just I am not using that part, this normalization part, okay. Here 1 by square root of 4 pi etcetera, okay. So, these are constant term. So, only I am using this theta, phi and R dependent part. So, here in this case one exponential term is there, So, that is basically e to the power, it is R dependent, basically I think some constant, I think that is z, I think I should write it is basically R by n a0, this I think z, okay, some constant terms are there, but it is mainly e to the power minus R dependent part, e to the power minus R, and then R dependent another part R to the power L, okay, and then polynomial in R, right, polynomial in R, okay, in R. So, this polynomial, as I mentioned that what is the form of this polynomial, that we know. Legendre polynomial, right, associated Legendre polynomial. So these are the wave function for hydrogen like atom, okay, and their form is this. Okay. Now, so basically for increasing n and l, so these polynomials are there. For increasing n and l, so these polynomials, form of these polynomials are basically complicated, but for first few values of n l and m, so these form of these polynomials are is simple. And let me, so for this first few values of n l and m, so what are the value of this wave function, what are the values of the, what is the form of this wave function. So that let me show in a table. So for first 3 values of n, so in table I have shown you here the form of wave function. So what is the form of wave function? Psi n l m, psi n l m, okay. So what is the complete wave function for first 3 values of n, means automatically for values of n what will be the L value and ML value, that we will know. So that already you know that for n equal, for n L is basically 0, 1, 2 up to n minus 1. So minimum value of L is 0 and maximum value of L is n minus 1, and for a particular value of L, this basically m value is basically yeah, so 0, plus minus 1, plus minus 2 is up to plus minus L. Okay. So now first 3 value of n means n equal to 1, n equal to first few value of n means n equal to 1. What is the value of L and ML? L equal to 0 and ML equal to m equal to 0. Okay. M equal to 0. M equal to 0. So for that what will be the wave function? For that what will be the wave function? So m equal to 0, m equal to 0. So this is 1. So this part is 1. Okay. And for L equal to 0, L equal to 0. Okay. For L equal to 0 and corresponding m equal to 0. So this theta 0 0 theta. So what will be the that will be also it will be 1. If I see the whatever polynomial I have shown you earlier, so this form of polynomial, I think I have yes. Yes, so polynomial, this the Legendre polynomial. So first we will, yeah. So here I have so Legendre polynomial, so associated Legendre polynomial. So P11 is given here, P11 is given here. So P0, say okay, P0, there is 1 basically, P0, PL, L equal to 0. So automatically m equal to 0, m equal to 0. So that this form of associated Legendre polynomial is it's related with this this PL. Okay. So P0, that is basically L equal to 0, it is 1. So this part also will give you, this part also will give you the 1, this part also for theta 0 0 it will be 1, this is 1, and for n equal to 1, L equal to 0, L equal to 0. So, r to the power L, r to the power 0, this is 1. Okay. So, basically this e to the power minus z r n a 0. Okay. And from these polynomials, it one has to see it comes 1 basically. I can show you it also comes 1. If you see this table, it also comes 1. Okay. This is Legendre polynomial, yes, L 1 1. So, this is the 1 or minus 1. Okay. So, this thus psi 1 0 0, psi 1 0 0. So, this one, this part 1, this is also 1 or minus 1. So, only this part left. So, that is why it is here one can see this psi 1 0 0. It is the, so this is the normalization, from normalization part it comes. So, I am not giving trace on that, but this is the exact normalized value for this wave function. So, this only r dependent part is left, e to the power minus r. Okay. So, it changes exponentially, okay, with r, this psi value psi 1 0 0. So, similarly you have this you can for n equal to 2, n equal to 2, n equal to 2. So, you will have L equal to 0 and 1, 0 and 1, okay, and corresponding m value will be for L equal to 0, this is 0, and for L equal to 1. So, this will be 0 and plus minus 1. So, 0 and plus minus 1, okay, and for that you have a function now psi 2 0 0, psi 2 1 0 and psi 2 1 plus minus 1, and its form is like this. Okay. So, these are constant term, forget them, but here you can see this it is 2 minus r z r by a 0 of course, and exponential of e to the power minus r z r by 2 a 0, because it was n a 0. So, this for n equal to 2 2, and here it is for 2 1 0. So, this term is there, this now it is this z r, it is basically r e to the power minus r, only r dependent minus r, and now cos theta term is there. Okay. Similarly, for psi 2 1 plus minus 1. So, here this term r e to the power minus r, this in this case sin theta. So, this is the theta dependent theta part, and then there will be phi part, because e to the power I m phi. So, now here m equal to plus minus 1. So, that is why it is e to the power plus minus e to the power plus minus 1. So, plus minus I phi. Okay. So, these are the few wave function, eigen wave function for hydrogen like atom. So, this for n equal to 1 and then n equal to 2. Now, for n equal to 3, n equal to 3. So, L will be 0, 1 and 2, and for each L again you have m value. Okay. And now, you will get psi 3 0 0. Here I have not written this factor, I just mentioned here some factor and this is the r dependent part, this is the r dependent part. Okay. And here psi 3 1 0, okay, factor, this is the r dependent part, okay, and this is the theta dependent, no phi dependent, but because m equal to 0 means e to the power I m phi. So, that will be 1. Okay. So, similarly psi 3 1 plus minus 1. So, it will have r dependent part, then cos theta term, and then factor, no cos theta, this factor it will be repeated, but it will be sin theta dependent and it will have phi dependent. Okay. So, similarly psi 320 is the same factor will be here, and then theta dependent term sin theta cos theta e to the power plus minus I phi, and psi 3 2 plus minus 2 it will be same this factor, but this theta dependent part sin square theta and phi dependent part e to the plus minus I 2 phi. So, from here what we are seeing, what are the important, what are the remarks we can do from this wave function, that for L equal to 0, for L equal to 0, for L equal to 0, okay. So, ML automatically ML will be 0, M will be 0. Okay. So, L equal to 0, so that is basically S orbital L equal to 0, this is basically S orbital from different orbits, means from for different n value, n equal to 1, 2, 3, whatever we have shown. Okay. So, L equal to 0, this is S orbit, and in case of S orbit, so this is basically S orbit, it is independent of theta and phi, only depends on r. Then this is S orbit, okay. And here also you can see it is independent of theta and phi, okay. But this one is p orbit L equal to 1. Okay. So, p orbit depends on theta, it has r dependence, but it depends also on theta, but independent of phi. Okay. And then other part also this when ML equal to plus minus 1. So, it has theta dependent as well as it has phi dependent also. So, here you can see that for L equal to 0, it is independent of theta and phi. For L is not equal to 0, it depends on theta as well as in some cases is phi. Okay. And here also you can see this is L equal to 0, psi 300. So, it is also independent of theta, but all other cases L is not equal to 0, it depends on theta. Okay. L is not equal to 0 means p state, d state, etc. Okay. And so if I plot this wave function, okay, so one can find out this how this wave function varies as a function of r, theta and phi. Okay. But it is since it is 3 dimensional, 3 coordinate r, theta, phi, so it will be slightly complicated, drawing will be complicated. Okay. So, instead of drawing this plotting this psi in Lm, if we plot just individual wave function of that is r n l, then theta Lm and then phi m. So, then it will be more convincing, more easy to understand. So, let us see if we plot wave function r n l as a function of L as a function of r, how this wave function varies with r. So, that we will see next. So, I think this table will be useful for plotting. So, I can so this basically this the part I got. Then next I will this the polynomial, I do not need them basically. Okay. So, before plotting the psi, or RNL, so you are, let us see about the probability. So, as I already mentioned in quantum mechanics, this it's difficult to tell the definite value of an observable, but one can tell in terms of probability, possibility to find a particle at a position, or to find the momentum of the particle or energy of the particle. Okay. So, what so here I have the one. Okay. So, here as I mentioned that we will instead of plotting this wave function as a whole, so we will plot this R n L, which basically it will tell the R dependence of the wave function. So, if we plot this one, so it will tell about the theta dependent part of the wave function, and this will be phi dependent wave function. But this so the behavior of wave function as a function of r theta phi, that is one thing, it gives some information. Okay. But to get more information, that basically we get from the probability density, and that probability density is defined by psi star, that is the probability. Okay. If psi is the wave function, psi star is the probability, okay, to find the particle, at a particular position, or to find the momentum of the particle in a particular position, etc. Okay. So, this instead of this plotting psi, so we will plot it, it will give some, what it will give, that we will see, as well as this is also more important, psi star, one has to plot psi star. So, that is the basically probability or probability density. Okay. So, that is probability density. Also one has to plot to get information. Okay. So, this is the probability density for hydrogen like atom, this is the probability density. Okay. Probability density is defined psi star psi. Okay. So, that means we have eigen function psi n l m. So, this star psi n l m. So, that is basically in terms of, we are getting this 3 part R n l and R n l star theta l m star phi m star. Okay. So, psi star means this, and then other part is psi. Okay. So, basically here you are getting R n l star R n l, okay, theta l m star theta l m, phi m star phi m. Okay. So, this probability density for 3 coordinate we can study separately. Okay. So, one is radial part, so we are telling that radial probability density, that is P r, we have written here P r. Okay. Radial probability density P r equal to R n l star R n l, equal to, one can write this also, R n l R square. Okay. So, P or what is P r then, or P r dr is the probability of finding electron at any location between r to r plus dr along a given direction, r to r plus dr along a given direction. So, radial probability density P r, okay, it is basically to find a particle along a particular given direction at distance r, So, that is basically P r, and P r dr is basically at a given distance, given direction. What is the probability to find the particle at any location between r to r plus dr. Okay. So, that is the P r dr. Okay. So, this is the radial probability density. Now, not radial probability density. So, it can be expressed in other way also. Now, this is this P r dr we have written along a given direction between r to r plus dr. What is the probability? Okay. Now, if I define another parameter, that what is the probability to find a particle between two spherical cells, the spherical cell of radius r and another sphere of radius r and another sphere of r plus dr. So, what is the probability to find the electron between these two spherical cells? Okay. So, that is to get the probability density for that type. So, that is, if we write, that is d n l r dr. So, here basically psi star d v, okay, because here theta and phi also that we have to consider this as a whole. So, within this volume, between two spherical cells within this volume, what is the probability? So, that I am coming later. So, here if I define this d n l r dr is defined as psi star d v, that is volume, elementary volume, if I integrate over this whole volume. Okay. So, what will happen? So, here theta part, it basically its angle, if I change angle 0 to pi, okay, theta, phi part if we vary the angle between 0 to 2 pi. Okay. So, it will have then this, I can write from here, we have seen this r n l square, theta l m square, phi m square, okay, and this elementary volume r square sin theta d theta d phi dr. So, that already I have discussed earlier. So, here if I integrate over theta and phi, not over r, then I can write this r n l square, it is basically r n l square, r square from here, r square, this I am keeping r square dr, and this theta and phi part if I integrate 0 to pi and 0 to 2 pi. Okay. So, this is giving me this is giving me 2 and this is 2 pi, this is basically 4 pi, and here normalized part I have not written. Okay. If I write the normalized part, so this 4 pi will go. Okay. Here we have not taken normalized part. So, you remember this for phi, it was 1 by square root of 2 square root of 4 pi. Okay. So, if you square it, okay, because phi m square, so it will be 1 by 4 pi will come. So, this here 4 pi, so it will go. Okay. So, that is why basically, so here d n l r square d n l r square. Okay. So, what is the meaning of this d n l as a function of r? This is basically the probability of finding electron between spherical shell, as I mentioned, between spherical shell of r and r plus dr. Okay. So, it is theta among for all theta and phi direction, but distance between radius between r and r plus dr. Okay. What is the probability? So, this is the PR difference between PR dr and dr dr. Okay. So, this the in one case along a given direction, what is the probability between r plus dr, and another case dnl function of r dr, that is the that is the probability to find the electron between two spherical shell of r and r plus dr, or if I leave this dr. So, the dnl r is basically the finding the electrons between spherical shell of unit width. Okay. Unit width. Okay. dr is now unit. Okay. 1. So, of unit width at r. Okay. So, these are the density probability or probability density. So, to find the electron, what is the probability to find the electron when we are going away from the nucleus? So, means at different distance from the nucleus, what is the probability to find the electron? Okay. So, that is DNL tells that one, DNL tells that one, okay. And DNL depends on RNL, and RNL, what is the form of RNL for different value of n and L. Okay. So, that we have seen RNL, it depends on what? Exponential term e to the power minus r, that is one part, and r to the power L, and then Legendre polynomial. Okay. And first few polynomial from the table we have seen. So, basically these are the RNL. Okay. This is the RNL. Okay. Okay. It depends, it is so first one n equal to 1, it depends on, it is basically exponential, it changes exponentially. So, if I plot it as a function of r, so this wave function will be like this. So, RNL basically it has exponential part, and then r to the power L term and this Legendre polynomial. So, if I plot it, what you will see, n equal to 1, L equal to 0. So, wave function explicit form of the wave function that we have seen, this, it will vary like e to the power minus r, right. It will vary e to the exponentially decay. So, it is exponentially decay with r. Okay. So, similarly for n equal to 2, L equal to 0, what is the form of RNL? So, what is the form of RNL? N equal to 2, L equal to 0. Okay. So, this is the r dependent part RNL. So, it has the same explanation as well as this another term is linear term is there. Okay. So, now, so basically if you plot these two terms, if you plot just to show you, if you plot this term, so one is exponentially decay term, one is exponentially decay term. Okay. It is not 0, but it is move like this. Another this term is basically e to the power minus r term. Okay. And another r to the power, another 2 minus j dot by a 0, 2 minus r, another term is 2 minus r. So, 2 minus r means y equal to mx plus c, y equal to mx plus c, right. So, in our case y is basically RNL. In this case it is n equal to 2 and L equal to 0, n equal to 2 and L equal to 0, n equal to 2 and L equal to 0. Okay. So, this we are plotting r to 0, and then your that is the y. Now, x is in our case r. So, r is here minus z r by a 0. So, minus z r by a 0. Okay. So, minus r. So, m x. So, this is the m negative slope, it is the negative slope, and plus c means here 2, plus c here 2. Okay. So, if you plot this one, so what will be the, so it will cut positive at 2, it will cut positive this 2, right, c, and positive y axis it will cut like starting from, for r equal to 0, c is 2. So, it is a here or here somewhere, okay, whatever, depending on value, whether it is normalized value or not. And this negative slope means slope is not like this, it is negative slope, it is a negative slope, it is like this, I guess. Okay. Okay. Negative slope is like this. Now, if you multiply them, what will get, what will be the form. So, it is basically, I can show you. So, it will be like this. So, it is following exponentially, okay. Exponential is high value. So, this negative r, it is 2. So, it will have some value. So, now this plus this, so it will start from say here. So, here, okay. So, here. So, its value is adding, so going up slightly. So, it will be like this, okay. And now, here it is basically negative. So, here it will come and then it will be like this, you know, it will be like this. So, it is going to exponentially, okay. So, it depends, here I have done this, it can be like this also. So, depending on that it varies basically this way, okay. 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 So, that is why here it is the r 2 0 is like this, okay. Similarly, r 2 1 one can see and one can plot, okay. Now, this probability, if I plot probability to find the electron between two spherical cells, this is the probability, okay. So, one can plot, one can get this, why one can get this from here, what about the r, so we have to make square of it. So, you will get basically because here why it looks like this. So, r 1 0 square. So, this basically this square is this, it is more exponential because e to the power minus 2 r now, okay. So, it will fall sharply, but with that r square term is there, with that the r square term is there. Now, r square term means is the, it will give parabolic, you know, okay. Whatever this we are getting, whatever this we are getting r 1 0 square. So, it will be more sharper exponential because e to the power now square term is there, e to the power minus 2 r, earlier e to the power minus r, now minus 2 r. So, it will be faster and then multiplied with r square, okay. So, you will have another I think parabolic term r square, y equal to r square, okay. So, it will be parabolic. So, it is this kind of things will be there, okay. Now, if I multiply these two, so 0 and this if you multiply, so it will be 0, okay. Now, here 0 and this value, so it will be also towards 0. So, that is why this it will vary like this, it will vary like this. So, that is why I have drawn here, okay. That is why I have drawn here like this. So, So, this way one has to plot, this way one has to plot this wave function, and you can see this wave function is varying like this, but their density probability, radial density probability, okay, it is varying like this. So, I will discuss more on this issue, because you can get the physical information from this plot. So, let me stop here. Thank you very much.